SwayamPrabha. Digital India. Educated India.
If you notice in the earlier lecture, we have discussed about the root locus, how the root locus can be changed with the variation of the system gain. So we have discussed the graphical representation of the movement of the poles of the closed loop control system with the different values of the system gain. If you notice here what you have done before, we have done this practice with the variation of the one single parameter. So the root locus what you have done with the variation of one single parameter, which is basically k. We change the k and how the locus has been drawn. This is what we have looked at. But in practically, this one single parameter cannot specify all the performance of the system. So this variation, it is not possible to satisfy all the performance specifically using a single parameter. So to solve this problem, we need to come up with some different kind of compensation which can be added to the control system to meet this performance or this specification what the designer has. So we need to consider to add some form of compensation to the control system to meet the design specifications. And this compensation we can add in form of electrical circuit, mechanical device, or electromechanical compensator. So the compensator may be electrical circuit or mechanical device or electromechanical device. Devices to improve the system performance. And these compensator, if you look carefully, this compensator basically adding the poles or zeros to the system in feed forward or feedback path. So basically, the compensator has a transfer function which adds poles or zeros to the system. So now, before we proceed to the control system, let's look how our root locus plot going to behave with the addition of poles and zeros to the system. So before we proceed, let's look the effect of addition of poles or zeros to the system. Let's go with a simple example. Then it will be clear how the system going to be affected with the addition of poles and zeros. Example, construct a root locus for the transfer function GSHS equal to K by S into S plus P1. So there is no zeros in the system, only there are two poles, one pole at origin, another pole at S equal to minus P1. And examine how the locus going to be affected by the addition of the following to the original transfer function. So let me go through this following. What are the addition we have to do? The first addition is we'll add a simple pole and we'll see how it will be affected. The root locus will be affected. Simple pole. Second case we'll consider multiple pole. And third case we'll consider simple zero. So we'll add this simple pole, multiple poles, or simple zero to this transfer function. To this transfer function we'll add. So we'll see solution. If you look the original transfer function, we have GS HS equal to K upon S into S plus P1. And if you see these poles location in our S plan, we have one pole is here and another pole is here. It is equal to 0 and is equal to minus P1. And if you go back to our concept of asymptotes, the angle of asymptote should be, it is clear that there should be a breakaway point will be somewhere here. That is quite obvious what you have done from the previous lectures. This is, there should be breakaway point here. And this, once the breakaway happens, the locus will go to infinity since there is no zero in the system. So it will go to the zero infinity. And now let's look what angle this locus will depart from this breakaway point. The angle of asymptotes will be, if you denote pi, so it will be 2q plus 1 n minus n into 180 degree. And since there is two poles, we can, there will be two angles. One is 90 degree and another is 270 degree. So it is quite obvious the locus will follow the asymptote. So locus will be something like this. Something like this. So this is the original transfer function, how the locus will be plotted for the original transfer function. Now let's look the case, first case. If we add simple poles to the system, how the locus will be affected. Let's look. Now, if we add a simple pole S plus P2, for example, to the GS Hs. So now GS Hs will be K upon S into S plus P2 and S plus P1. So this will be the modified transfer function. And if you plot these poles in S plane, if you place these poles, we have one pole at origin, another pole is here, another pole is, for example, this is minus P2, minus P1, and S equal to 0, for example. And this is the location of the poles of the transfer function, 1 by S into S plus P1, S plus P2, right? And so if you notice here, the angle of asymptote will change. So in this case, there will be three angles, and one locus will, we can calculate the angles easily, you can calculate. So there should be breakaway happens between these two poles, and locus will be going to like this, and there should be another locus will be going this direction like this. It means, what is the takeaway from this addition of poles? We can write here, very interesting here. So it means the root locus will bend into the right half plane. So it means which limits the range of K for the system to be stable. But in the previous case, if you notice here, for any values of K, the locus is always on the left-hand side. The system is stable. But in the second case, if we add a pole to the system, so we have limits on the range of K. So system is going to be less stable, for we can't take any values for K. So that's why system going to be So there will be different part. One is stable region, another is the unstable region for the different values of K. Now, let's look at another condition. If we add another pole, what will happen? The second part, multiple poles. If you add another pole, for example, let's assume if we add a pole is equal to minus P3 to GS HS, what will happen? So in this case, our transfer function will be GS HS equal to, can write 1 upon S into S plus P1, S plus P2, S plus P3. And if you place these poles in S plane, you'll have, well, this is my S equal to 0. This is, for example, let's assume this is S equal to minus P3, for example. And this is S equal to minus P2. And this is S equal to minus P1, for example. So it is quite obvious there will be locus in between, and this is also there will be locus in between these poles. And in between these poles, there will be breakaway somewhere here, and there will be angle of, there will be some, some locus will be like this, and there will be another locus, something will be like this. So if you can do this experiment, if you take some example with some numerical values of P1, P2, P3, you'll have locus something like this. So what is the takeaway from this part? The addition of another pole adds another branch that goes to that goes to 0 infinity. But the system can still unstable if the system gain K exceeds head. So in this case, again, the system will be unstable if you increase the K after this part, after the imaginary axis. So in this case also, there are the limits on K on which the system will be stable. Now let's look how we can get the root locus plot for the addition of the 0. Before we proceed to the addition of the 0, let's have a note here. Interpretation. So for the above analysis, the root locus plot bend towards the right half plane with the addition of focal to the OLTF, open loop transfer function. Hence, the addition of a simple pole tends to destabilize the closed loop control system. This is very, very important part, this part. How if we add the poles to the system will be, it will be tend to the destabilization. So this is very, very important part. Now, let's look how the root locus will be look like if you add pole zeros to the system. We'll consider the original system. Original system we have GS HS equal to K upon S in S plus P1. And let's add to this transfer function a simple zero. Let's add a simple zero is equal to G1, for example. And the transfer function would be GS HS K into S minus G1 and S into S plus P1. And if you locate these poles and zeros in S plane, we'll have, here we have, there is another pole, let's consider P equal to minus P1, and we are adding a zero here, S equal to minus G1. And if you notice, there will be breakaway between these two poles, and a break-in will happen here. This is quite sure. Now, the root locus, it will be breakaway somewhere in between this point, and it will go like this. So it means if we add zero to the system, system will be more stabilized. For any values of K, the locus always in the left hand side. And if you take another case, if you add a zero in between these poles, let's consider another case. This is, for example, S equal to 0. If we add a 0 here, S equal to minus C1, and if you have pole here, S equal to minus P1. So in this case, for the locus from this pole will end here, and locus from this pole is equal to minus 4 will go like this. So in both the cases, in this case and in this case, locus actually stays always in the left hand side. It is not going to the right half plane. So we can conclude from this part, we can write here with the addition of zeros to the system, the root locus plot to bend further into the left hand plane. So hence we can write by adding a zero to the system in the open loop system, the closed loop system will be more stable than the original closed loop system. So what is the takeaway from this lecture is if you add zero to the system will be more stabilized. And if you add poles to the system will be tend to the destabilization mode. And based on this motivation, we'll be in the next lecture, we'll be discussing the concept of compensator to the system, how the compensator going to add different stability criteria to the original system. Thank you.